Now let's talk about conditional probability. Conditional probability is something that we need to use when we have events that are not independent. So knowing that one event has occurred will change the probability of another event. So first let's talk a little bit about notation. The probability of the event B occurring, given that the event A has happened, is written like this. Okay, the way we write this is probability of B, and then this vertical line is said given A. So probability of B given A, meaning we know A has occurred. What's the probability of B now? Okay, so let's do an example. What is the probability that two cards drawn at random from a deck of playing cards will both be aces? All right, so what we're going to do is this is probability of the first card. First is an ace. Okay, and the probability of the second is an ace. Now, these are certainly not independent because if I draw an ace, the first card I draw is an ace, then the probability that the second is an ace is actually going to be lower than what I would have expected because now there's only 3 aces left. And so we can write this as saying, well, I need to take the probability that my first, is an ace, and then multiply by, the next thing is the probability that the second is an ace, given that the first was an ace. Okay, that's the way that this works. And so, well, the probability that the first card I draw is an ace is there's 4 aces out of 52 cards, and then times, and now if I know that my first card was an ace, the probability that the second card is an ace, there are 3 aces left, and there are 51 cards left. Okay, and so this was a little bit different than what we would have done for independent events. Okay, and so now we can go ahead and multiply these, and this turns out to be 1 out of 221. Now let's do this using the chart. Find the probability that a randomly chosen person has a speeding ticket given they have a red car. Okay, so this is the probability that they receive a speeding ticket, so ticket, given red car. All right, so now we're going to actually kind of use just the basic probability formula here. We know that the person has a red car. That means that we know we are stuck in this row here. Nothing outside of this row actually matters. So the probability of having a ticket is, well, there's 15 ways that a person with a red car could have a speeding ticket. So that's 15. And then divided by, well, the only possible ways that we could have a person with a red car is 150. So this would be divided by 150. So this is 1/10 or 0.1. Okay, for the next one, we want to find the probability that a person has a red car given they have a speeding ticket. So this reverses it. This says now I know a person has a ticket. What's the probability they have a red car? And so now I'm actually stuck in this first column, okay, because I know that the person has a speeding ticket. Well, how many ways can a person with a speeding ticket have a red car? 15. There's 15 people that had a speeding ticket that had a red car with speeding tickets. And so there's 15 ways that can happen. And then divided by the number of ways I could have a person with a ticket. So I look at my speeding tickets and I see there's 60 people with speeding tickets. And so divided by 60. So this is 1/4 or 0.25. Let's formalize this. There's a beautiful formula for conditional probability. The probability of B given A is the probability of A and B divided by the probability of A. Okay, and you'll see that we could actually rearrange this formula. If we multiply both sides by the probability of A, we end up with the probability of A and B equals, and then the probability of A times the probability of B given A. This is the AND formula that we use for all events. Okay, no matter what, whether or not they're independent. Okay, let's go ahead and use this formula. If you pull two cards out of a deck, what is the probability that both are spades? Okay, so the probability that this is an AND, this is A and B. Probability of first being a spade and the second being a spade. This is going to be equal to the probability that the first is a spade times the probability that the second is a spade, given that the first is a spade. This is very similar to our aces example that we saw a few minutes ago. So the probability that we draw a spade, well, there are 13 spades out of 52 cards. And then times. Now, if I know the first card was a spade, the probability of getting a second spade is there are 12 spades left, and there are 51 cards left. And so now I can multiply these together. And so let's see, 13 times 12 over 52 times 51 will be 1 over 17. If you draw two cards from a deck, what is the probability that you will get the ace of diamonds and a black card? So, probability of ace of diamonds, that's a wonky diamond, and a black card. Black. All right, so this is an and we're going to use what we just did, which is this is the probability of the ace of diamonds times the probability of a black card, given that you have the ace of diamonds. So the probability of drawing the ace of diamonds. Well, there's one ace of diamonds, and there are 52 possible cards. Okay, and then we are going to multiply by the probability of black if we know that we've drawn the ace of diamonds. So the number of black cards is 26. However, if I know that I've drawn the ace of diamonds, there's only 51 cards left. Okay, and so I multiply these together, and the 26 over 52 turns into 1/2 times 1 over 52. That's 1 over 102. Okay, here we've got home pregnancy tests, and it turns out that home pregnancy tests are not perfect. Okay, they can give what are called false positives or false negatives. So here's a chart for 93 different women that took a home pregnancy test, whether or not they were actually pregnant and whether or not the test showed that they were pregnant. So let's do this first one. Let's find the probability that a woman is not pregnant if the test result is positive. Okay, so probability of not pregnant given a positive test. Okay. So let's use our definition here. The probability of not pregnant given positive test. This is the probability of not pregnant and a positive test. Positive test divided by the probability of a positive test. Okay. So the probability of not pregnant and positive, this is right here. Okay. 5 out of 93. 5 out of 93. and then divided by the probability of a positive result. Well, there are 75 positive results out of the 93. 75 out of the 93. Now you'll notice the divided by 93 is going to cancel out here. We just end up with 5 out of 75, or 1 out of 25. And this actually always happens when we have our table with our probabilities here, okay, when we have the conditional. These two things will always have the same denominator, which means you don't actually need to do the probability, you just need to do the number of ways it can happen. Okay, let's do that. Let's take that shortcut for the next one. The next one is the probability that the test result is positive. Okay, so probability of a positive test given that the woman is not pregnant. Given not pregnant. All right. So this would be, okay, the probability of positive and not pregnant, divided by the probability of not pregnant. Now, like I said, we don't actually have to do the probabilities. We can actually just do the numbers of ways it happens. So the number of ways of a positive and not pregnant, positive and not pregnant, is 5. So we just take 5 divided by the probability of not pregnant, meaning the number of ways that we had a not pregnant person. And that was, there's 19 non-pregnant. So 19. So that's the probability that we have a positive test when the woman is not